Everyone, we are continuing with circular motion, but actually taking a step backwards and seeing how the force of gravity, something that while we've talked about in passing, we've never really explored in detail, but how that actually is related to circular motion. So kind of two things jam-packed in this video, the basic and general idea of the gravitational force and how that applies to circular motion, of course, our focus in this sequence of videos. Okay? So to start us off, this thing known as the universal gravitational force. To be honest, in this class, almost since day one, we've been using this, that the weight of an object, or maybe you called it F with a little g, whatever it was, the weight of an object is equal to the object's mass times g, where g was 9.8. That, to be honest, was a cheat, or a simplification. Okay, that was for things on Earth. But gravity is a force that affects everything in the universe that has mass. It's in fact one of the few what's known as fundamental forces. There's only actually a handful of very fundamental forces, one of them being the electromagnetic force. That's the force that's like holding atoms, molecules, molecular bonds together, holds your table together, even your body together. Gravity is another fundamental force, all right? It is a force that's always attractive, and it's between things with mass. So here it is right here. I mean, let's just look at it. This is the fundamental force of gravity. It is based on g, which I'll talk about in a second, and it's a force that's always between two masses, always. It's an attractive force between two masses based on the size of those masses, and r, where r is the radial distance. They don't use d because if you think of like things orbiting one another, you know, the distance is kind of always changing as things move around. So r, the orbital radius, it is just a measurement of distance, how far apart these two things are located. Okay? Now, first I want to say, technically this radius is measured from the center of two objects. Like the universal gravitational force between the Earth and the Sun should be measured from the center of the Sun to the center of the Earth. That's the radius you should be plugging in here. Okay? Now, when you think about people standing on, say, planet Earth or a tree on Earth, it is technically also from the center to the center of the object, but oh my gosh. The radius of the Earth is so big, and this little symbol right here, this sometimes is used to show the symbol for the radius of the Earth. The radius of the Earth is so giant, if you were to use this equation for, like, you standing on the planet, just use the radius of the Earth. You don't have to worry about the extra, like, meter. It's insignificant. Here I have the value for the radius of the Earth. It is so much larger than your own little radius to the center of your, say, belly button. Just use the radius of the planet. But otherwise, and it should be obvious, it should be what's given, it's the distance between the two objects. That's the radius that goes in here. We're not really going to worry about positive or negatives, even though technically it is a force. Again, because these objects are always moving in a circle. So you're just going to find the value of these forces. You're going to plug in the value for the radius and, of course, the masses of the objects. Now, of course, we measure mass in kilograms. We're still going to measure radius in meters. G is a constant, okay? It is a constant that works everywhere in the universe when you use this equation. It's not like it's just for here on Earth. But whenever you use this equation for g, you're going to plug in 6.67 times 10 to the negative 11th. This number is given. You don't have to memorize it. It's on the AP Physics 1 equation sheet. Okay, you don't have to really memorize these units either, but always 6.67 times 10 to the negative 11th. Because this number here is so small, maybe you recognize that when it comes to relatively small things, you, me, the table, even like a house, this force of gravity is really tiny. Technically, there is a force of gravity between you and your computer or your TV if you're watching this on TV. But those masses are so tiny, all right? The force value is insignificant, puny. You don't feel yourself being gravitationally attracted to somebody as they walk past you. Technically, there is a force, but it is so small. You need huge things on the scale of asteroids, planets, stars, galaxies, for this force to be noticeable. So yeah, it is universal. It is between everything with two masses, or between everything with mass, but it's very small for things on kind of our scale. Here, this equation right here, this is what you're going to see on the AP Physics 1 equation sheet. Again, they use absolute values because you don't really have to worry about positive or negative, okay? G, m1, m2 over r squared. They don't put the g in the numerator, but it's obvious. It's just being multiplied. You don't have to memorize some of these values, but depending on your class, you might be doing some problems where you need to know the mass of the Earth, the radius of the Earth. They'll be given to you on any exam or quiz from my class. College Board would give you these numbers, but they're, common enough that you might want to jot them down in your notes, okay? So that's the basic idea. That's the force of gravity equation. All right, it's more general. It can be used universally, whereas this one is just for the planet Earth. You can't use this between, say Jupiter and the sun. All right? Well, next part B, the acceleration due to gravity. Something that also we've talked about before. We've used g equals 9.8, but actually, again, team, that is also a simplification. That is also us actually cheating a little bit. G, acceleration due to gravity, is actually its own little thing. And even for astronomers, it has much more significant meaning outside of just how quickly things accelerate here on Earth. The force due to gravity equation, this big thing, when we look at G and the mass of the Earth and the radius of the Earth, what I have here in this blue box, this is all stuff for us here on the planet Earth, right? Okay, if you were to calculate this, you were to take that constant that we saw on the other slide, take the mass of the Earth, m1, and divide it by the radius of the Earth squared, what you get is, there it is, 9.8 meters per second squared. That's where that number comes from. It's us actually simplifying. That's why we could get away with this m times g. M is this mass right here, your mass, the mass of the car, the mass of the tree. And g, well, that's just what you get when you plug in the values for Earth and the constant into this equation. Again, that's why this equation doesn't work universally. That's where g is coming from. Okay, you would use a different set of values for, say, calculating the acceleration due to gravity on, say, Jupiter. Continuing on with our discussion about this acceleration due to gravity, something that we've kind of been taking advantage for. Again, the acceleration for any planet is actually known as this lowercase g. Not just for Earth. It will have different values depending on whether you're on a comet or the surface of the sun, if that was feasible. Okay, but astronomers use this value for other things in the cosmos, not just for planet Earth. Okay, the acceleration due to gravity is in fact even given its own equation. Remember, this is what we use to find it for here on Earth. In general, this is the equation for the acceleration due to gravity for any object, any planet. You use that constant. M is the mass of that planet or star or black hole, okay, or galaxy, if I guess you wanted to do it that far out. And the radius, the size of that thing. Now, to be honest, this is the very common way this equation is written out. The acceleration due to gravity for an object, gm over r squared. This is what's conventionally known. If you were to use this equation on one of my own exams, an exam in a college course, they would certainly know what you're talking about. However, the AP Physics 1 equation sheet doesn't use this equation anymore. It kind of annoys me. They use this equation. This is what's on the AP Physics 1 equation sheet. Again, I bet on the AP exam you can use this. In fact, I'm sure of it. You can use this and the graders will know what you're talking about. But they use this version. Again, it's the same thing. Because notice, remember how I said it's gm over r squared? There's that g, there's that m, there's that r squared. Well, this is saying that g is the force due to gravity, so this whole thing divided by m. That would divide out this thing. A little silly. I don't think it's as, helpful in this form, but this is what's on the AP exam. Again, you could be asked to calculate what's the acceleration due to gravity on Jupiter, and you would use this equation or this one. Okay, same kind of thing, same difference. Okay? Now, something that's a little weird, g is not only known as the acceleration due to gravity, it's referred to as the gravitational field strength. We have never used that in any of my prior videos, but it is pretty common, and you might see that phrase on the AP Physics 1 exam. So you kind of, unfortunately, just got to know, if it's asking, what is the gravitational field strength of the moon? Well, you would be doing this calculation. You would be calculating the acceleration due to gravity using the equation that's given that we've now gone over, okay? So a different set of terms, okay, but it means the same thing. It's the same idea, okay? And it's still showing the acceleration of an object. In fact, it's also in a way a little more useful for, say, astronomers. Like, if I told you that the force of gravity on an object on, I don't know, Saturn was 200 newtons. That is actually not a very helpful number because the force of gravity is based on two different masses, right? The mass of Jupiter, the planet, the thing, and the mass of the object. Actually, looking at g, astronomers use this a little more often because if you think about it, what it's saying is it's how much force is on an object for a given chunk of mass. All right, that 9.8 is actually a little more useful because here on planet Earth, that tells us exactly how much things accelerate. Okay, that's the amount of force per, say, kilogram. In fact, the only other thing I want to say on this slide, not only is g sometimes referred to as a different term, gravitational field strength, the units, While certainly meters per second squared, it's an acceleration, is valid, you could also see it represented as force is newtons, so newtons per kilogram. Oh my gosh, weird stuff, just throwing more terms at you. You might also see it represented as newtons per kilogram. Maybe it says Jupiter has an acceleration due to gravity of 5 newtons per kilogram. That's a wrong number, I just made something up. But that is the value of G, okay? A little weird, and I'm sorry it's tough, but those are some terms that are used both on the AP Physics 1 exam and if you continue on in your physics career, okay? Next part C, gravitational fields. This is actually going to go pretty quick, I should say. Still based on this idea of acceleration due to gravity or gravitational field strength. First, what is a field? Because we haven't talked about it. We're not actually going to get too in depth, but these diagrams could show up on the AP Physics 1 exam. A field shows the direction and strength a force is acting. For example, here is a representation of, I don't know, a park someplace outside here on planet Earth. These big downward arrows, they represent the strength and the direction of the force due to gravity. And this should not be surprising. We know every single time we've drawn a free body diagram, we had the weight of an object acting down. Weight acts straight downwards, right? Well, imagine I take a ball or something and I release it from rest right here. What's it going to do? It's going to accelerate straight down. It's going to feel a force straight to the surface. If I place an object right here, same thing. If I place an object right here, same thing. If the object is released from rest, this is also kind of showing the path the object would move in. Of course, if I threw an object like a baseball, the free body diagram would still look like a force straight down, and this is showing the direction of the force, or the acceleration, that would be acting on this object. This is a representation of the gravitational field for the surface of the Earth, okay? Well, if you zoomed out, because, again, we're looking a little bit more universally, Earth is, of course, much closely a sphere, not just a flat surface. The force of gravity always points inwards. So this is actually a more general diagram for the gravitational field for the Earth. Again, same idea. If I was an astronaut and I was able to just place at rest an object right here, gravity would tug it inwards and it would move close. I just realized my face is kind of being blocked, so I'm going to move my floating head. Aha, now I'm up here. But the same idea applies. Now, it gets a little more complicated if we look at a couple different objects because the moon and the Earth both have their own gravity. And what is this diagram showing but the relationship? For example, if I release a little object right here, the Earth is much bigger, about 6 times more massive. It has a stronger gravitational force. So if I release a mass right here, it's going to get pulled to the Earth. But if I release a mass way closer to the moon, even though it might feel a little bit of a tug from the Earth, it's so much closer to the moon that the moon is going to win this battle. If I release something right here, this is a little interesting. Both the Earth and the moon would be kind of pulling it downwards, right? Because both these objects are below, so to speak. But again, the Earth is a little more massive. It has a little stronger tug. It might feel a force and a directional path in that direction. What do you think this represents right in the middle? If I was able to place an object at rest right here, this is in fact where the forces balance between the Earth and the moon, and it could conceivably stay at rest relative to the 2 other objects. Now, you're not going to have to draw these on the AP exam, and to be honest, we don't spend a whole lot of time with them in general, but there are some general rules. Notice these lines, they act towards the mass, okay? The lines are always pointing toward the mass. It represents the direction of the force towards massive objects, right? You don't have the lines cross, because that would be a confusing way to diagram these things. Lines always hit the surface at perpendicular angles. Not super important that you memorize that, but it is how you're always going to see it, okay? And something that's maybe a little helpful, if the lines are closer together, if they're denser, like notice right here, the lines are denser, that represents a stronger force. And that should make sense because the force due to gravity and that acceleration due to gravity, right, it's based on R. When R is smaller, the force and G are larger. So you could symbolize that. You could showcase that with lines closer together. So just by looking at this picture here, look, it's obvious that the force due to gravity is stronger here because the lines are closer together than when you're over here. And that's true based on the equation for the force due to gravity or the acceleration due to gravity. Okay, so you might see these diagrams, they're representing the direction and the strength of gravitational fields or the force due to gravity. Okay? All right, last bit of our video. Oh my gosh, we're still going. I had to move my head again. Oh my gosh, now I'm over here. Hold on. we're going to see how this applies to circular orbit. What does it mean for actually things moving in, say, an orbit around the Earth or around the sun? And I'm actually going to start by showing a little simulator right here. So this is representing the sun. Here's the sun. This is the Earth right here. Okay? Now these blue arrows, they represent the force due to gravity, Fg, right? GMM over r squared. Notice these arrows are pointing in opposite directions and they're the same length, they're the same size. Does that make sense? It should, because by Newton's third law, the sun is pulling on the Earth and the Earth is pulling on the sun. This green arrow is representing the velocity. And the Earth, while it is in fact a little bit more of an ellipse, it's very close to a circular orbit. And in this class, we will simplify orbits to circular paths. This green line represents that tangential velocity, and it makes sense, right? It's tangent to the circle. The Earth has inertia. It would love to fly out in a straight line, but the sun is pulling it inwards. This is circular motion. Centripetal force still applies, centripetal acceleration. Now, there's no string, of course. There's no roller coaster track. What is the force responsible for the Earth moving in a circle? It's now the force due to gravity, okay? Oh, that's how we can apply circular motion now to things a little bigger, things in orbit, okay? So let's see what that looks like. I have this mass M right here. Let's draw a free body diagram for this mass M, okay? Well, there's a force pulling inwards towards, it looks like this is ME. That usually means the Earth, but let's see. I have a line like that. I'm going to call that FG. All right, I wouldn't want to use the label W. I certainly wouldn't want to use mg because this is different, right? This is more broad. This is the universal force of gravity. And that's it. That's the only force that's acting on this planet. Okay, let's set up this sum of the forces. Now this object's moving in a circle. So this is the sum of the forces in the centripetal direction. There's only one force and it's acting towards the center. So that would be Fg, and that equals mac, and that would of course be the mass of the object times v squared divided by r. Okay? Now, what is the force due to gravity? Oh my gosh, it's G. The mass of the big thing, that's ME. The mass of the smaller thing, that's just M, divided by R squared. That's equal to MV squared divided by R. Something maybe you notice, look at this. The mass of the thing that's orbiting, this, say, moon or satellite or astronaut, that actually cancels out. If you were solving for the velocity, let's do that. I'm actually going to move a little over here because my head is in the way. If I was solving for this velocity, I'm going to swing an r to the other side. That's going to cancel out with one of the r's that's down here. So that's going to leave me with g me divided by r equals v squared. And then I'm going to take the square root because I want to get rid of this v squared. I'm left with v equals the square root. I'll put that in a second. GME divided by R. Oh, there's an equation for the velocity of this orbiting thing. It turns out it doesn't actually depend on the mass of that orbiting thing. It only depends on the mass of the planet. This is a pretty well-known equation, okay? Though I'll warn you, if you're in my class, you should be able to prove this. This is not necessarily a fundamental universal equation. It comes from Newton's second law, using the force due to gravity for things moving in a circle. It's a quick proof, but you should be able to show that, okay? Okay, the last thing I'm going to show you, I know this is a long video, but this is an important topic, and this more or less covers the main ideas for several variety of problems. I still have my setting up the sum of the forces in the centripetal direction, okay? But now, let's again plug in, as we've done a couple times, this idea that velocity is also 2 pi r divided by t. If I plug that in for velocity, I have g times the mass of the Earth, or the mass of the big thing, okay, times the mass of the thing that's doing the orbiting, divided by r squared equals m. Now I'm going to square everything. That's a 4 pi squared r squared divided by t squared divided by r. Or if I simplify that, GME, I'm going to cancel out the masses, so those masses disappear. Okay? I'm still going to keep my r squared for now. That equals 4 pi squared. R squared here and r here is going to leave just 1 r divided by t squared. I'm going to do one more step. I'm going to bring the period to the left side of the equation, and I'm going to bring the radius that's down here to the other side. So that's going to leave me with t squared, still multiplied by g, times the mass of the big thing, the Earth in this case, but the thing that's being orbited around. That's going to equal 4 pi squared. I'm going to swing this r squared over, but there's already an r. So r squared times r, that's r cubed. And this is actually a really important equation in physics because G and M, that's just a constant. This is the constant, of course. This is just the mass of the orbiting thing. 4 pi squared is constant. For a given thing, the Earth, the Sun, the period, the time it takes an object to move around it is related to the radius of that object. It's a weird relationship, t squared related to r cubed, but this is known as Kepler's third law. Johannes Kepler in the 1500s came across this observation in the year like 1500. Okay, based purely on observation. He watched things observing, came up with all this data, and derived this relationship. Isaac Newton, 100 plus years later, just using his own laws that he came up with, bam! He proved it using pretty simple circular motion stuff. Technically, Kepler's third law is not on the AP Physics 1 exam, but this idea, using centripetal forces, using now this universal force due to gravity, allows us to learn about how things move in the cosmos. It allows us to determine certain values, how long it takes things to orbit, how far things are away from their orbit. And if you're in my own class, we might touch upon that. And of course, you would learn more if you built upon this in astronomy classes or other physics classes. Long video, I know. A lot of information, but important information. That's it. I'm signing out. Thanks a lot for watching.